Okay, good morning. So we continue the lesson. I'm going to teach you in the next part of combinatorics. That's called r-Permutations. But before starting the new lesson, I would recommend you to start this warm-up problem. Okay, so this is something that in principle you should be able to solve it. It's a little bit hard question. Not very hard, but a little bit hard question. I want to give you time to think about it. So we solve it, and then we start the new lesson. Okay? And by the way, is the question clear? Yes? So you have the word mailbox. You want to consider all permutations that you can make using the letters in this word, but with two constraints. First of all, A and M has to be adjacent. By adjacent means immediately next to each other. But in the meanwhile, B and X shouldn't be adjacent. Okay? So at least there should be something between them. So with these two constraints, we want to solve, because if I don't give the constraints, the question is clear, yes? 1, 2, 3, 4, 5, 6, 7 distinct objects, so it becomes 7 factorial. Okay, so I will wait for you. Okay, any opinions? Yes? You can just give me the number or the answer. Yes.
360.
Ah, you are fine. I don't know the number, but so let me write 360. But how did you think about the problem? Any other numbers? Yes.
I put should I explain?
Yeah.
Okay. I put the A in one box.
Mm-hmm.
Then I made A in one box, and then I made 3 other boxes where I, O, and L would be. And then I counted the spaces between them to see where B and X could be. And then I just multiplied them.
Are you happy with what you have done? So that is important. You have to have a clear algorithm in mind so that you make sure that you're really counting what you are counting. Yes. Any other ideas? I don't want the details, but the ideas. Okay, so let me ask you one question. Let us stop up to here. This you should be able to solve it easily if I don't have this part. So in how many permutations of the letters in the word mailbox are the letters A and M adjacent? That's it. Let us see how we can solve this. This is not a hard question up to here. So how should I do that? I would say that I want to put M and A in one box, as you said. So I would have something like this. I put A and M. So I will choose a box, but I know that in this box, I only put A and M, okay, in some order. And then when I take M and A out, there are other letters left for me, I, L, B, O, X. So how many objects I have in total? 1, 2, 3, 4, 5, 6. So I can arrange them. Stage number 1 is to arrange them in any way that I like. So it becomes 6 factorial. But now, wherever I see my box after this stage is done, I start filling the box by letters M and M and A. How many ways I can do that? 2. So then I multiply by 2. So this is the total number of ways that I can arrange these letters and be certain about that A and M are adjacent. Yes? But of course the problem becomes a little bit more interesting if I want to add one more constraint to it. Because you know that in this calculation, I have also considered the permutations in which B and X are next to each other, which I don't want to have them. So how do you think about the problem?
I don't know. I removed the B and the X, and then I counted the spaces of where they could be, like between the rest of the letters.
Yes. Okay. Because the algorithm that you're talking about, I have to be very alert to understand what is going on. And I have to make sure that you are not missing something. But if you are certain you can do your calculations, I can do my calculations, and then we compare the answers. If the answers are right, it means that your algorithm is definitely right.
I did something wrong, but
Okay.
I think we
Yes?
You can find all the permutation where b and x are next to each other, and take 6 factorial times 2 minus the number that's b.
Yeah, so the complement rule somehow. Yes, that is the correct idea, because this only cares about if A and M are next to each other. It doesn't care anything about that. So what we do is this. I don't know if I draw a picture for you here. So let us say that this box includes all, yes, permutations, all permutations in which A and M are adjacent. Yes, let us consider all items. I write this in the box, but this box can also be partitioned into two groups. I'm not saying groups of equal sizes, but I can partition it into two parts. Some of these permutations in which A and M are adjacent have also this property that B and X are adjacent. Okay, so here B and X are adjacent. One part is that B and X are not adjacent. But be careful, the whole box contains the ones that A and M are already adjacent. So from this, I can group them into two different groups. The ones that B and X are adjacent, the ones that B and X are not adjacent. Okay, so do you agree that the question mark of the problem is the number of items here? This is the question mark. Why? Because in this part, B and X are not adjacent, and in total, A and M are always adjacent. So that is exactly what I want to count. Okay, we were able to count all the items in this box because the only constraint for the permutations in this box is to have A and M next to each other. And that is this number, yes? So this becomes 2 times 6 factorial. This is the total number of items in this box. But now I want to consider the total number of, okay, so now I want to count this part. Can you tell me how should I count this part? How many constraints are in this part? One constraint from the beginning, A and M are adjacent. Another constraint for this part, B and X are also adjacent. Okay, so I need to count this question mark. So how can I count this question mark? It is simple again, yes? Because now I want to put B and X next to each other and A and M next to each other. So how many boxes I need this time? I need 2 boxes, yes? So let me put one box like this for putting A and M there, and let me just draw another, I don't know, box like this for putting B and X there. Okay, so, and then I have also I, L, O. Yes? So how many objects I have now? 1, 2, 3, 4, 5. So how many ways I can arrange them? Stage 1, arranging them 5 factorial ways. But now I have A and M to put them in this box. I can do that in how many ways? 2 ways. And then after I put them in one order, I also want to put B and X in this box. In how many ways I can do that? Another 2. Yes? So hopefully you agree with me, this becomes what? 5 factorial. So the question mark is this one minus this number. Do you agree?
Yes.
So that's the answer. This is one possible answer. Of course, I can calculate this. I don't think it is hard. Let us try to simplify it. You don't need to simplify if I haven't mentioned that. You have to. But if I want to simplify this, how do you do that? For example, instead of 6 factorial, what do you write? You write 6 times 5 factorial. Yes, is that understandable? And then I have minus 4 times 5 factorial. But 2 times 6 is 12. So it becomes 12 5 factorial. And then I have minus 4 5 factorial. So what is the answer? I have 12 of them. 4 of them are gone. So 8 5 factorial. Yes, so this is the answer, and it is much bigger than that one, because 5 factorial is 120, and then if you multiply it by 8, it becomes 960. So the answer, if you want, so there are 960 items in which A and M are adjacent, but B and X are not adjacent. Any questions? That was just a warm-up problem. Hopefully you refresh your memory. But now today we want to talk about r-Permutations. What is the meaning of r-Permutations? So this, let me make it a little. Okay, so here if I want to describe it for you. So far, let us say that I have 4 letters. Okay, and then I ask you how many permutations you can write using these letters. The answer is simple, so you can just write 4 factorial. Okay? But now let us say that I don't want to use all of them. Let us say that I have 4 students, but I have 3 jobs for them. Okay, so job number 1, job number 2, job number 3. I want to see that in how many ways I can assign a student to each one of these jobs. Yes? So then you understand that I have 2 kinds of choices. One choice is that, first of all, which students to choose. And then after choosing, let us say I choose a student A, B, and C. One way is to assign job 1 to student 1, A, B here, C here, or the other ways. So I have more degrees of freedom, yes, in my choices and in my arrangements. When I talk about use all of them, then you have just the choice of arrangement. But now that if I want to find a sub-collection of them and arrange them, then I have 2 degrees of freedom. 1 degree of freedom is that which students to choose, and then after I chose them, which jobs to assign them. So it means that the order somehow matters as well. Okay, so the word permutation always means order matters. Okay? So that is different. For example, let us say that I want to choose 3 students, just go to cinema together. Then there are no locations and positions, yes? So I just choose them. That is a combination problem, because in that problem, order doesn't matter, yes? If I choose Jafar and Samir and Parham, it doesn't matter in which order I am choosing them. We want to go to cinema. So that is a combination problem. Still, we haven't talked about that. Yes, we are talking about permutations. Permutations means that order matters. The only difference from the previous context is that in the previous context, we use all the objects, but now we want to use a sub-collection of objects. Okay, so if I have n objects, I want to choose r of them and arrange them. And r is a number between 1 and maximally n. Then the item that I write is called an r-permutation. So for example here, let us solve a simple problem. How many ways I can choose 3 students, okay, and just assign these jobs to them? So one possibility is so let me write job 1, job 2, job 3. One possibility is this one. Is that understandable? What does it mean? It means person 1 gets this job, person B gets this job, person C gets this job. But I have a lot of other options without even changing the combination yet. Yes, I can write A, C, B. This is a new situation for me, because even though the students involved are the same, the jobs are different now, yes? So I need to consider all of them. So how many things I can consider? A, B, C, and then I can write B, A, C, B, C, A, and then C, A, B, and then C, B, A. But of course, you see that this is not the only cases. I can change the combination and do the same thing. For example, instead of choosing A, B, C, from the beginning, I can choose person A, person B, but person D. Okay? This item is a new item. It is not repeated in the previous cases. Okay? But still for this one, I can write a lot of things, yes? I mean, a lot of things here means how many things do you know?
6 more.
6 again, yeah, 6 more, yes, because I can write A, D, B, and then I can continue. So each one of these items that you see, each one of these items is called a 3 permutation. Permutation, yes. Okay. So I want to know how many 3 permutations are there. Okay, one way is to write them down and count them. One way is to come up with an idea. So let us make sure that you understand what is the meaning, yes? If I ask you how many permutations are there, full stop, it means that write all possible arrangements of all 4 objects. But now I am asking you how many 3 permutations are there. It means that you are allowed to choose 3 of them and then arrange them, yes? So I'm asking you how many possibilities I will have this time, okay? We want to find an idea how to count this. Yes?
Can we use a product rule?
Yes, that's the product rule. It's the most simple one. But because this is very famous in combinatorics, we use the product principle to answer this question once for all, and then we find the formula. From now on, we try to use the formula. Of course, there is no objection if you want to solve the problems from scratch every time, but that is not a good option. Okay, so can you answer me? In principle, I could have asked you this question in the very first lesson of this topic. So how many 3 permutations are there? Yes?
Still 4 factorial?
But how?
Because
So you want to write the 3 permutation.
Yeah.
So how many stages you think about your task?
2 stages.
Why 2 stages?
3.
So you want to have a 3 permutations. So how many locations you need to write down a 3 permutation? 3 locations. Yes? How many options are available for the first location?
4.
All 4 of them, you can put them here, yes? And then how many are left for you for the second location? 3. And this 3 is independent which one you have chosen. So product principle is applicable so far. And then how many options are there? 2. So, and this 2 is independent of my choices here and there. So this is the answer. So it becomes 24. Yes? Okay. Let me ask you about this. How many 2 permutations are there? This time, how many locations you need? 2. For this one, how many options you have? 4. For the next one, independent of how I have done this? 3. So there are 12 options. Okay? But now let us solve this problem in its generality. Let us say that I have n distinct objects, but I want to choose a collection of them. Let us say r of them, which is less than n. And then I want to see how many permutations are there. Okay, so let us solve this problem in general. So I have n objects. So let us say that I have object number 1, object number 2, up to object number n. And let me say that r is a number which is minimally 1, maximally n. Okay? And then I want to write an r permutation. It means how many locations I need? R locations. So location number 1, location number 2, location number 3, and then I continue this list. The last one is location R. The previous one is location R minus 1. Yes? And now let us try to see how many ways I can fill them up. How many options are available for location 1? N. Any one of these objects I can locate here. So this is N options. But I choose one of them and put it here, and then I go to location number 2. How many options are available now? N minus 1, because the only thing that I cannot choose is the one that I already chose. Yes? So it is N minus 1. Is that right? What is the number of options for the next one? N minus 2. Okay, so then I want to answer this one. Can you fill up these two? Yes? No, because I have R objects. If R is equal to N, yes, that would be N. But in general, don't imagine that you have a sub-collection of them. Depending on R, these numbers are different. This one N minus R? Okay. How many of you agree with this one? N minus R? If you say this is N minus R, then what is this one? N minus R plus 1. Yes? So what you are saying, if this is the case, because you know that when you go from right to left, you are subtracting 1 unit at a time. It means that when you go from right to left, you are adding 1 unit at a time. So if your guess for the last one is this, then definitely your guess for this one should be this. Yes, that's correct. But this is not correct. What is the correct one? Yes?
N minus R plus 1.
Yes, this should be here. Yeah, so this, I will clean this, and then I would write this is N minus R plus 1. And then the next one, of course, becomes what? R plus 2. Okay, why this is the case? Let me describe it for you in this way. I don't know. This is the first location, but what is subtracted from N?
0.
Nothing, 0. Another name for N is N minus 0. This is the second location, but what is subtracted from N? Not 2. N, 1 is subtracted. Yes? This is the third location, but 2 is subtracted. So if I have the rth location, what should be subtracted? R minus 1 should be subtracted. Yes? And then when I open the pair of brackets, it becomes minus R plus 1. So that's the case. The last one is this. Is that right? Okay, now if I ask you the question mark, what is the answer? The question mark is the product of these numbers. So n times n minus 1 times n minus 2. And then you continue this list, n minus r plus 1. That's the answer. So that is the number of r permutations of n distinct objects. And there is a symbol, even on the calculator for it. And this symbol is denoted by P, capital letter P, and then you put N and R. Okay? So this is the number. This is not the permutations. This is the number of permutations. This is the number of R permutations of N distinct objects. So, number of R permutations of N, let me emphasize, distinct objects. Yes? So this is a formula. If someone asks you, do we have a formula for this? Yes, we just derived that. So the formula is N times N minus 1, N minus 2, and then you go up to N minus R plus. Yes? But this, I can use the factorial symbol to write this more compactly. And that formula, you have it in the formula sheet as well. Okay? But how can I do that? This is not n factorial, because n factorial is starting from n minus 1, and go up to 1. But it usually doesn't reach to 1, depending on what the value of r is, yes? So this means that if I want to write it as factorial, this is the trick. I would write it as n times n minus 1 times n minus 2, and then I continue this list. So far, I have copied and pasted the same thing, but now I multiply this by the list of all previous natural numbers to this. So what is this? What is the smaller one? What is the next one if I want to keep the order? It is n minus r. What is the next one is n minus r minus 1. I start subtracting until I reach to 3, 2, and 1. Then I stop. But of course, I have multiplied this here to compensate for that change. If I want to respect the equality meaning, I have to divide by the same thing. So what happens? It becomes divided by n minus r minus 1. You have to have a little bit of imagination, yes? If I ask you, what do you see in the denominator? You see that the product of all natural numbers starting from 1 but going up to n minus r. So what's the meaning? N minus r factorial. So then it becomes n minus r factorial. Yes? And now if I ask you, what do you see in this long list in the numerator?
N factorial.
The product of all natural numbers is starting from 1 up to n. So it is just n factorial. Yes? And this is the compact formula that you have it in the formula sheet. And if you have a calculator, this symbol is also there. So you have this formula finally. The number of permutations, the number of r-Permutations of n distinct objects is equal to n factorial divided by n minus r factorial. Of course, this symbol only makes sense if what happens? If r is between 1 and n. Yes? I hope that you agree with me that this symbol is not meaningful. Yes? But of course, it doesn't mean that you don't see this in the book. But do you understand this is not meaningful? What is the meaning of this? This is the number of 0 permutations of n distinct objects. It means that I have n distinct objects. I want to choose none of them and arrange them. So it doesn't make sense. Yes? So this is why the minimum value for r should be 1. Yes? But before doing any calculations, what is your guess about this number? What is your intuition? Let us read it again. This is the number of n permutations of n distinct objects. What this number should be?
N factorial.
N factorial. Yes? So you know that this should be n factorial. Okay? And now let us calculate this using that formula. So what happens? I want to calculate p, n, and n here. So instead of n, I put n. Instead of r, I also put n. Yes? Then what happens? It becomes n factorial. This becomes 0 factorial. So then we have to have a convention for it. So that's why I'm saying that it is a natural choice to agree that 0 factorial is 1. Why? Because this is what we expect from our understanding of permutations. So we know that p and n should be n factorial. On the other hand, this formula is predicting that p and n is this one. So then I have a little bit of problem that what 0 factorial is. Yes, I can define it whatever I want, but if I want to make life more comfortable for me, I will say that 0 factorial is better to be defined 1, because then I don't need to explain all the time p and n is n factorial. So this is why one of the reasons that this is defined to be 1 by convention. Because then, if this is defined another number, what should I do? Let us say that I don't want to define this, I want to define it to be 2. Okay, then what happens? Then it means that this formula is valid up to n, but not including n. For n, I would say that if r is n, don't use this formula, go back to the previous notion. But if r is n, if r is less than n, then use this one. By having this convention, I can go up to n without any problem. So that's a very good choice. Okay, so now you at least have understanding why people have chosen 0 factorial to be 1. Yes? Okay, so that is one thing. Okay, let me ask you one question to test your understanding. What do you expect for this number to be, Pn1? First of all, what is the meaning? The number of 1 permutations of n distinct objects. So imagine you have n distinct objects. Your duty is to choose one of them and arrange them. Yes, Nazan, you want to say something? No? Yes? It's n. Yes, because if I have n objects, I want to choose one of them. As soon as I choose that one, the arrangement is already done. There is nothing to arrange. So it means that Pn and 1 should be n, if my understanding is correct. But let us double check it using this formula. So let us calculate Pn and 1. What happens? Instead of n, I still put n, but instead of r, I put 1. So it becomes n minus 1 factorial. Can you simplify this? Yes?
You can write n factorial as n
Times.
times n
Yes,
minus
yes.
1 factorial.
N factorial means multiplication from 1 up to n. I can write it from 1 up to n minus 1 and then multiply it by an extra factor n. So n factorial can be written as n times n minus 1 factorial, and then I divide it by n minus 1 factorial again, whatever this number is, and that one are cancelled. So you see that what you get is according to your expectations. Yes? So we could guess Pn1 is n. We also calculated it is really n. Is that clear? Okay. So this is a new model. I want you to have it in mind. So I know that you can use the product principle all the time, but it becomes hard if you want to start everything from scratch every time. So what this model tells you? Okay, so let us try to understand this from distributing marble in boxes. That's a good model in combinatorics. Okay, so let us say that I have n marbles labeled 1, 2, 3 up to n, but I have only r boxes. The boxes are also labeled. This is an abstract model to have in mind. Whenever your problem can be reduced to this distribution problem, you need to use Pn and R. Okay, what is the problem? You have n distinct objects. These are marbles labeled, so it means that you can recognize which one is which. And then you have only R boxes. The boxes are also distinct. They are labeled. But the number of boxes is less than or equal to the number of objects. And of course, you have at least one box. Okay? Whenever you want to choose R of them and put exactly one in each one of these, then you are facing this model, that r-Permutation model. Okay? The answer of this, if I ask you how many ways you can distribute these marbles inside this box so that in each box there is exactly one marble. This is this model. Is that right? So every problem might be not abstract. This is an abstract model. You can have a problems, I don't know, in real life. But if that problem can be imagined through this lens, then you have this distribution problem, and that is r-Permutation. So what is the answer to this problem? In how many ways I can distribute these marbles inside this box so that in each box I have exactly one marble? The answer to this is what? N. Yes? But let us change the setup. This time I have n marbles. Sorry, I have r marbles. 1, 2, up to r. But my boxes are more. Yes? So I have n boxes. 1, 2, up to n boxes. Still I have the same condition between these numbers. This time the number of marbles is less than the number of boxes. Now I want to distribute these marbles inside these boxes so that each box receives at most one marble. What is the answer to this problem? So let me just review. Here, I have more marbles than boxes. I want to distribute these marbles inside these boxes so that in each box there is exactly one marble. I am claiming the answer is this. We come back to it if you don't understand it. But now I change the situation. This time I have less number of marbles than the boxes. My question is that in how many ways I can distribute these marbles inside these boxes so that each box receives at most one marble. Of course, it is clear that I cannot fill them up, all of them, yes, because the number of marbles is less. But either I leave one of them empty, or at most that box should receive one. In how many ways I can do this new distribution? Are you with me? Is the question clear? Okay, so yes. Yes, Samir.
P, N, and R, you can rethink of it as distributing boxes to marbles.
Marbles. That's the same story. Okay, but this so that is also P, N, and R. Yes? I don't know, for some psychological way of thinking, we prefer to distribute marbles in the boxes, but from mathematics point of view, marbles and boxes are objects, so it doesn't matter which one you assign to the other one. So do you agree that this is the same problem, only I'm changing the role of circles to boxes? But that's the same answer. If you don't like this, let us think in that way. How many ways I can so how many boxes I can assign? So here, let us go back here. If I want to start from the product principle, this task of distributing these marbles into these boxes can be done in how many stages? R stages, yes? R stages. What do you call the stage one? Stage one is assigning a marble to the first box. Stage two is assigning a marble to the second box. In how many ways this can be done? N minus 1. And for the reason that I described, the last one is n minus r plus 1. So that is this product, the answer to the problem. Now let us consider this distribution. Okay? This distribution can also be viewed as a task in how many stages? Again, R stages, but you have to have this paradigm shift of thinking, yes? So what is the stage one? Again, I can do this in R stages, but what is the stage one? Yes, assigning a box to a marble, yes? So how many ways I can do the first stage? Again, n, yes? After one of these boxes is assigned to this marble, I want to assign a box to the second marble. How many ways I can do that? N minus 1. And for the same reason, the last one is this one. So you see the answer is the same. Okay, but I want you to think in that way. Both these kinds of distribution problems are having the same answer, and that is P, N, and R. So it doesn't matter if your objects is more than the number of locations, or the number of locations is more than the number of objects. Yes, so have this model in mind. Is that clear? Okay, from now on, there are two types of problems. One problem in the book is not dealing with counting, it's just dealing with the formula and algebra. So that's also one possibility. Okay, so let us try to start solving some examples that are relevant. Okay, before going that, I want to explain this one. This is meaningless if I want to describe something to it, but we can calculate it. So if you see this in the book, don't interpret it as counting problem. But if someone asks you what this is, you can calculate it by pretending that the same formula also is applicable to this case. But this doesn't make any sense if you want to interpret it as counting problem, because then it means that I have n objects, I want to choose 0 of them and arrange them. It doesn't make sense. But if I want to assign a number to this, which number is good to assign, follow the same formula. But instead of r, I put what? 0. So this becomes n factorial over n minus 0 factorial. But n minus 0 is n. So it becomes n factorial over n factorial. So you can say that people define this to be 1 again. Yes? So that's also a definition or a convention. It doesn't have any meaning. Yes? Exactly like 0 factorial, it doesn't have meaning. It's a good convention. That's also a good convention. Okay, so let us try to solve some problems. So this is the word that I want you to concentrate. I have the word keyboard. So if I ask you how many words I can construct using the letters in this word, how many? Yes, you just see that all of them are distinct, so you count them 1, 2, 3, 4, 5, 6, 7, 8, and the answer is simply 8 factorial. But now if I ask you how many 4-letter words you can construct using the letters in this word. So the answer is, you don't need to give me the final answer. If I ask you to do the final answer in the exam, I will be explicit. But now just say something, yes? Or you so the number of, what did I say, 4-letter words? 4-letter words. So you say that I have how many objects? 8 objects, but I want to choose 4 of them, and arrangement is important, order matters. So that's a permutation problem. So the answer is simply this, that's it. If I insist what that number is, then you can calculate it. Let us also calculate it in this time. So how should I calculate it? I have the formula in formula sheet. Instead of n, I put 8. Instead of r, I put 4. So this becomes 8 factorial divided by 8 minus 4 factorial. This means 8 factorial divided by 4 factorial. Yes? But if I insist to calculate that, how do you calculate it? A little bit simpler. I will not give you these big numbers to calculate without calculator. But in principle, you can write it as 8 times 7 times 6 times 5 times 4 factorial. That's good to start. Because whatever 4 factorial is, the denominator is the same, so these two are cancelled. Yes? And then, of course, this is 30 to 110, and then it becomes this. Yes? So it is not hard. But this is important. Don't continue. You just continue until that factor that it can be eliminated. We don't need to continue more. Okay, so that's the number. So is that clear? Okay, so let us try to solve this problem now. Do you remember we had this problem before? So let us say that I have 10 people. 1, 2, up to 10. Okay, in how many ways I can arrange them? 10 factorial. So now the question is that, if you remember, 3 of these people, they don't want to be next to each other, none of them. Okay, so P1, let us say P8, P9, and P10. This doesn't want to be adjacent to that person. This doesn't want to be adjacent to that person. These two, they don't want to be adjacent. In how many ways I can do that? We solved this problem before. Do you remember that? What was the good algorithm for that? You don't remember, yes? So these models you have to remember. Because if you don't remember, it means that you are really solving that problem from scratch again. Okay? So, okay, just think a little bit. You have some experience now. Yes?
Factor the spaces in between
Something like that. But I would say that, okay, do you remember this word? You know, the people who are actually making troubles for us, we don't care about them for the time being. I will put the other people, and then I put some spaces between my people and then put them there, yes? So in how many ways I can arrange the other people? So I would say that I have P1 up to P what? 7. So I need how many locations for them? 1, 2, 3, 4, 5, 6, 7. So I will consider stage 1 is to arrange these non-problematic people. In how many ways I can do that? 7 factorial. Okay? Now let us assume stage 1 is done. What does it mean? It means that I decided about which person is where. For example, let us just keep one P2, P1, P2, I don't know, P3, P4, P5, P6, P7, P6, for example. For example. Now let us assume that this is done. Then, do you remember what was the trick? I was talking about these empty spaces that these people now make between them. And then I want to use these locations, some of them of course, to put these people there. Okay, how many locations I have? 8. These are my boxes. Yes. So these are my, if you want to say, boxes, and these are my marbles. And that is the distribution problem again. So this is a practical problem, but it can be modeled using that idea of distributing these marbles inside the boxes. But you know that each box should receive at most 1. So that is exactly according to that model. So when you can construct this in your head, find a connection, then you are relieved. The answer you already know. So what is the stage number 2? Stage number 2 is as if I want to distribute 3 marbles in 1, 2, 3, 4, 5, 6, 7, 8 boxes, so that each box receives at most 1. And that is exactly your model. You know the answer. So what is stage 2? Is P, 8, and 3. Okay, so that's why I want you to solve it in that way rather than going back and solve it from scratch. Of course, if you do that, that's completely okay. But then what is the final answer? The final answer is this number multiplied by that number. Most of the time, this is enough. If I insist, I have to give you a calculator so you can also calculate this. You calculate, you get the number. So this is why I'm saying that you have to have these models somehow in your memory and try to see that hard problems, how they connect to these models. And then if you can connect, then you know the answer. I'm not saying that this always works, but that is at least better than nothing. Any questions? No? Okay. So now let me So how many permutations of the letters of the word second? I want to wait for you this time, okay? We have a word second, this word, and I want to know how many permutations of the letters of this word are there such that the vowels are in even locations, okay? How many permutations? I'm not saying that how many 2 permutations, 3 permutations. I'm asking about the total number of permutations, but with one constraint. The constraint is that the vowels should be in even locations. Yes? So for example, is this an acceptable permutation for me by this constraint?
Yes.
Yes, because the vowel E is in the second location and 2 is even. And O, which is the second vowel, is in the 4th location. That's also even. So this is one of the acceptable ones. But of course, you can have other acceptable ones. So this is a very simple one. If I don't want you to solve it. You can do it in the exam. You can solve it from scratch using principles, product principle. But try to understand this new topic as well. So I want you to answer this using the topics, using the idea that we learned here. Is it easy or not? So how do you think about this? I'm telling you, I insist to use this new concept today. So how do you think about the problem? Anyone else? Yes? So from the beginning, how many locations I need for my permutations? 1, 2, 3, 4, 5, 6. Yes. So I know that I need 6 locations. Yes. Okay. Stage 1. What do you do for stage 1? Vowels in even locations. So you need to. This is good. I don't want you to write this down in the exam, but I really want you to say the story in your head. So stage 1, what you want to say is to do what? To put vowels in the even locations. Is this model you see or not? Because how many locations you have? Even locations, 2, 4, and 6. So the number of boxes or the number of locations is 3. But how many objects I have? I have 2 objects, here in this case vowels. And I know that each one of these boxes can receive at most 1. So it is exactly according to this crude model. So then you don't need to think because you know the answer. The answer is P of what? 3 and 2. Because and you don't know, even you don't need to remember. The bigger number comes first, the smaller number comes second. Yes? So here I have 2 objects, 3 locations, so it becomes P, 3 and 2. Yes? So this is the number of ways that I can fill up, I can accomplish stage 1. Now stage 1 is done. What does it mean? It means that I made my mind which locations I want to use and in which order. For example, let us say that I chose this one to put O and this one to put E. Okay? Then I know that these boxes are gone now because they are filled. And then how can I solve the problem? Stage 2 is, let us give Nazan this opportunity, yes? Others. Other numbers are the consonants, yes? S, C, N, and D. And then I have 4 objects, and how many locations are left for me? 4. Some of you think that I am not allowed to use this. No, this is not the case, yes? So I have 4 locations, 4 objects. That is the model we learned before. So what is that one? 4 factorial, stage 2. Yes? So in total, because I want to accomplish my task, this can be done if both stages are done. So this means that I have to write this times that. Okay, and the calculating this number shouldn't be hard. But let us, for practice, do that. What is the answer? 4 factorial. How should I answer this one? 3 factorial in the numerator. The difference between them, which is 1 factorial in the denominator. But 1 factorial is what? 1. So forget about it. And then 4 factorial is 24. 4 times 3 times 2 times 1. And this is 6. So it becomes 144. So there are 144 objects, options. Yes? Okay. Another problem of this type. Using the letters in the word magnetic. Using the letters in the word magnetic. How many 5-letter words can one write down such that in each of them both of the letters M and A are used? Let me read it again. Using the letters in the word magnetic, how many 5-letter words can one write down such that in each of them both M and A are used? M and A are used, but I want to write 5-letter words. Yes? It's also a very simple question. So of course, what is the final number? Could you calculate the final number as well?
Wait, I just wanna, is it, you want us to write a 5-letter word?
Yes.
We're using these letters
Yes.
with M and A included.
Yes.
Isn't it just 5 factorial?
No. No, because I have more letters than 5. If I have exactly 5 letters and I want to use 5-word letters, that is 5 factorial. Final number? 240. Nazani? What? Okay. Any other numbers? Yes, do you want to give? What? Only 42? Okay. No? Yes? Okay. Okay. So I will take this off. Now, why you couldn't solve the problem? You know, the problems, the answers are super simple to write down, but it doesn't mean that the problems are simple. You have to follow what I told you. Try to break this task to several stages. If you don't do that, you might be able to find the answer, but that is a coincidence, I would say. You have to say this story to yourself. I want to do this task. I want to do it in through these stages. Now, what's your number? 1,000? 1,200. 1,200, you mean? Yes? Now that you want to change your opinion?
Yes, can you draw the
Yes. The formula, if it is there, I don't know, is it? Yes.
So 210.
210. Okay. Yes?
2,400.
Oops. So
Yes,
the numbers are actually
I got this.
oscillating. This one?
I got this.
So we have two words here. Yeah, I think you might make a mistake. Did you consider two cases?
I think so.
No, because when I say it includes M and A,
Or you can switch
Yeah.
it to 2,000.
so it should be that's the case. So be careful about these small points. Yes? So how do you think about the problem? Again, try to give this story to yourself. Okay, magnetic, I want to make a 5-letter word. So I know that how many locations I need? 5 locations, yes? 1, 2, 3, 4, 5. But be careful, these locations are distinct. You can consider them boxes or whatever you want to. But when I have some constraint, I don't know how your brain works, I will start going to get rid of these things that I have some constraints on that. So I know that M and A should be there. Okay? And then, so it means that 2 of these locations has to be dedicated to these 2 objects, and I know order matters. Is this one of these models that you see on the board? The number of boxes is 5, but how many objects you have? 2, and you know that each box can receive at most 1 object. And that's exactly the model. There's nothing to think. So what is a stage 1? How many ways I can do a stage 1? P, I have 2 objects, 5 locations. Which one should come first? You don't even need to think. The bigger one should come first. The second one is what? 2. This is already taken care of, the order as well. Don't think that you need to consider 2 other cases. One M comes first, A. No, this not only chooses the location, but also takes care of arrangement in the same time. Yes? This is the meaning of P of 5 and 2. I choose 2 of these and arrange it there. So the order is taken care of here. Okay, what is a stage 2? Let us say that the stage 1 is done. What is the meaning of a stage 1 is done? It means that I decided to choose 2 of these, for example, this one and that one, and I also decided to put, for example, A here and there. And now I want to arrange something else. What is that something else? M and A are gone from my list. And then how many options, how many objects I have? 1, 2, 3, 4, 5, 6. Yes? How many locations, how many boxes I have? 3. So what I want to do, the same story again. I have more objects than my locations, but each location can at most receive 1 object. So that's exactly the same model. So what is S2? Is again a P. P of what and what? 6 and 3. Because I have 3 objects, 3 locations, and 6 objects. And then the question mark is what? The question mark is P 5 and 2 multiplied by P of 6 and 3. Okay, that is good enough. Might be, this is in the options if I want to give you multiple choice questions. If it's not, you have to calculate it. By the way, this level of calculation doesn't need calculator, I think. So what is the answer? Follow the formula. 5 factorial goes to the numerator, 2 factorial, sorry, what is 3 factorial? Why? The difference between them should go there. Multiplied by this one, 6 factorial, divided by the difference between them is 3 factorial again. Okay, but that's not hard. 5 factorial is what? 120 divided by 6 is 20. 6 factorial is 100, is 720 divided by 120. So yes, 2400 is the correct answer. Yes? So that's also a problem. So you see that I am using the models. Of course I can start solving the problem using the product principle from the beginning. But I want you to don't do that, because if the problem becomes harder, then you will have harder time to do that. Yes?
Have you talked about what happens if you have two of the same letter?
No. That is, I wanted to do that and I erased that. That was a good idea because we will not be able to cover that. Next time we will cover it. That is called permutations with repetitions. Okay, so, and that's a good point. In all cases, you see that I do not have any letters repeated. So far, my examples. Okay, now this is one type of problems. Now, because we have also a formula, there is another type of problems that you might face. So I will give you two of them here. This has nothing to do with counting. This actually needs your algebraic skills. So let me give you an example. So let me ask you to solve the following equation. Example. I will also wait for you, okay? So solve the following equation. So solve the following equation. The equation is this: 2 times p n and 2 plus 50 equals to p of 2n and 2. When I say solve an equation, of course, I mean find n. So I am asking you find n so that this is satisfied. Okay, I want to wait for you. So this is the only formula that you need, nothing else. This is not a counting problem. You just need to use this formula in an appropriate way that you can find n. Could you do that? Yes, what's your answer?
N is equal to plus or minus 5.
Okay, minus 5, if that is correct, you should exclude minus 5. Because this symbol does not make sense if I have a negative number of objects. So this is something, first of all, no one needs to tell you that these should be integer. And if you, for example, get n equals to 1, that is also not acceptable. Because p1 of 2 is not defined. Yes? This number should be first. This first number should be bigger than the second number. And it should be natural. So if you find a number that doesn't satisfy, it seems like a false root again. Yes? So you have to eliminate that. Okay, but was it hard? It is not hard. You just need to use the formulas properly. So let us just do it as much as we have time. And then I would recommend you to write it down and then do it for the next time. But let us concentrate here. I want to solve the following equation. It means that I am supposed to find what n is. Okay, so the only thing that I have in my hand is that formula. So here I just copy and paste 2, but p, n, and 2. N is the same as n, but instead of r, I put 2 everywhere in the formula. So it becomes times n factorial, n minus 2 factorial, yes? And then I have plus 50 equals to, what should I write here? In the numerator, 2n is playing the role of n. So wherever I see n, I just write 2n. 2n factorial, and then I have 2n, but minus r. r in this problem is 2, and then factorial. So that is what you have to start writing. And then you know how to simplify things a little bit. So I don't know, I hope that you understand 2, you cannot pull 2 out. Yes, because 2n is one number and then you want to factorial that number. Yes. So what you do, you need to simplify. So what is the option to simplify? Instead of n factorial, what can I write? I can write n times n minus 1 factorial, but that is not good enough. I go one more step. It becomes n times n minus 1 times n minus 2 factorial. This is good to stop, because whatever this is will cancel that one. The same story happens for the next fraction. The next fraction, what can I write here? I can write 2n times the previous number, which is 2n minus 1. That is not enough if I want to put factorial here. I go one more step. The previous number is 2n minus 2, and then I put factorial. That is good. And then I divide everything by 2n minus 2 factorial, and then you see what happens. This, whatever this one is, that is the same, they are cancelled. Whatever this one is, they are cancelled. And then what I get 2n minus 1 plus 50. On the right hand side, what do I have? I have 2n minus 1. Yes? But I see that everything is divisible by 2. For simplicity, I divide everything by 2. Of course, if you don't do that, it will work, but it becomes harder. So I divide everything by 2. It becomes n squared minus n. This becomes 25. When I divide, 2 is gone. I multiply n in. Yes? So then I minus n and minus n are gone. So this means that minus n squared, I move this to the other side, this becomes minus 25. So this means n squared is 25. As you mentioned, it is better to write plus or minus 5, and then you say that the minus 5 is not acceptable. So n equals to minus 5 is not acceptable. Therefore, the answer is what? N equals to 5. But is 5 really acceptable? Yes. For example, if it was 6 here, and then you find 5, still 5 is not acceptable. Because this number should be greater than or at least equal to this number. Of course, in this case, 5 is okay, so this is the answer. Any questions? Okay, so I would recommend you to think about this problem. We will solve it in 2 different ways. Both of them are important. We will have it on next Wednesday. And then be prepared for the quiz. Take the quizzes seriously. Yes, and then it's only set theory, nothing else. Okay? Thank you very much.